We should see that meeting is being recorded at this point. Good evening, good afternoon, and good morning, depending on where you are worldwide at this point. This is yet another and a first nexMPI webinar in the new year 2026. All the best for the new year and all the best for nexMPI as a consortium. Today, we have Dr. Silva, who is basically a physicist with noticeable background in magnetic nanoparticles, hypothermia, nanothermometry, etc., etc. He's also a PI, principal investigator in Aveiro, in Portugal, and working basically on the interface between physics and chemistry, which makes it extremely interesting for today, because he's going to present fundamental principles and of magnetism, electromagnetism, and in relation magnetic particle imaging, etc. So without further ado, and please take a floor, share your screen, and start presenting. Thank you so much.
Thank you very much, Leila. Thank you very much for the kind introduction. So I hope that you all can hear me and you already can see my first slide. I'll come back to this and to the reason why I chose this slide. So I'm going to tell you very simple things today, but I think that sometimes it's good to go back to the simple ideas. And the first one is, okay. So when people realized about magnetic phenomena, so basically they start measuring attraction, repulsion, they came up with this framework of understanding that, which are the Maxwell equations. And so I think to imagine the Maxwell equations as the relation between two things. On one side, there are the creatures and which are the fields. And on the other side are the creators. And in the case of the magnetic field, the creators are the currents. So this is a density of current. This is a current. The creators are the currents, and the creatures are the magnetic field. So the classical view of electromagnetism is that you have a current, so a moving charge, which also appears here in this Lorentz equation. So there is a moving charge, and this moving charge is responsible for something that, let's say, exists in space, and which we call magnetic field. So magnetic field is a sort of a creature that extends throughout the space, and which is made, this creature, by the currents. So, okay, and the Maxwell equations, they just give a relation between the currents and the magnetic fields. And they basically say that the magnetic fields, they just curl around the currents. Wherever you have a moving charge, some sort of a current, let's say you have a magnetic field, and the magnetic field is something that curls around that moving charge or that current, which is different from the electric field. But I just put this slide here to highlight also a very simple idea, which is a magnetic field. I like to think about fields, electric and magnetic fields, in terms of this. A field is a density of flux. So you imagine something that is creating the field. I mean, in this case, it's the electric field. So here you have some sort of a charge, which is the creator. And then you have something that is a flux. It's not a flux like, we know about water flux, we know about light flux. So it's a sort of a flux in the sense that it's something spreading in space, but it has, of course, no matter associated with that. So it's something abstract, but I like to think about magnetic fields in terms of flux. So we would say that the currents, they create a flux, and the field is just the density of flux. And of course, we can manipulate this density of flux. We can make it, I mean, wherever in space it's more dense, it means that we have a higher field. Wherever it's less dense, it means that we have a lower field there. So, okay, it comes back, this framework comes back to the experiments of Ørsted back in this year, and then to the framework of Ampere, that just 6 months after the Ørsted experiment, he came back to this, basically to this law, just written in another terms. And as for the creators, for what is making this magnetic field, currents. And from the beginning, people, realized or divided this in two kinds of currents. Currents in the sense that there are moving electrons in a wire, just like Ørsted did, which people called the free charges, the free currents, and something that people back then called the bound charges or the bound currents, which is basically materials. People realized that currents like electrons flowing were producing magnetic fields, and also people realized that materials were producing magnetic fields. So they put the hypothesis that there were some kind of currents in these magnetic materials, and they call it bound charges. And so these currents here in the Maxwell equations, they are in general the sum of the free charges, electrons flowing in some conductor, and what they call the bound charges, which is related to the magnetic materials. So it took, here I have, so from the beginning, so people understood this in two complementary ways. So this is a handwritten note from Ampere, and so Ampere, so suivant moi, so according to myself, so he was thinking that everything was like currents, and currents were producing a magnetic field, which is basically perpendicular to this current. And at the same time, there was people like Monsieur Biot and Savart, which you probably know due to the Biot-Savart law, that were regarding magnetism not as currents, but as magnetic moments perpendicular to these currents. So in magnetism, we have this, this double way of regarding the things. We can regard this as a magnetic moment, or as a current associated to this magnetic moment. And mathematically, there is this relation between magnetic moment and a current that flows into a loop. And this also gives us, this is, let's say, the reason, it gives us the idea why in the international system of units, the magnetic moment has units of an ampere meter square. So a magnetic moment is a sort of a current that is flowing throughout an area. And that's the idea of, that's where magnetic moment comes. And of course, when we talk about magnetization is basically the volume density of this current. So basically, you come up with the units of ampere per meter. So from the beginning, there is this dual mode of regarding the creators of magnetism, magnetic moment, or an associated current. But of course, people didn't know exactly where these bound charges were coming from, because there was no evidence of a real current there. There was no heat dissipation associated to that, and it took until 1915 when Einstein made the concept of this experiment, and Haas put the experiment in practice, and they gave the first experimental proof of the existence of these molecular currents, of these bound currents. And after that, of course, people associated these currents to, here. So they associated this, of course, with the properties of the electrons. So, I mean, the protons and neutrons, they also have a magnetic moment, but the magnetism that we see in everyday materials comes from the electrons, basically because they have a lower mass, and the origin is their angular momentum. So the angular momentum, so associated with the electron, and the intrinsic spin angular momentum, they both contribute to a magnetic moment. And the relation is this simple relation here. It's, proportional to the charge and inversely proportional to the mass. That's why in the case of the electron, this angular momentum translates into a much higher magnetic moment than in the case of the neutron and in the case of the proton. Yes, the proton has a spin, yes, but it translates into a much smaller magnetic moment just because it's much heavier. So the creators are free charges, like, electrons going into a wire, and these bound charges, which are related to the properties of the electron in our case here. So this was 1915. So they realize, also the quantum nature of this magnetic moment. So once it's related to the angular momentum, of course, if the angular momentum is quantified, it's quantized, of course, the magnetic moment is also quantized. And the first evidence, so the first photograph of these spins was made here by Gerlach. So this is a very classic picture of the magnetic moment, where we are basically separated a spin ms plus 1/2 and minus 1/2 here. So that was the first time that people realized that there are energy levels associated to the magnetic moment and everything that followed that. Just one thing. So just because sometimes there are some, let's say, some misconceptions about what magnetism can do. So when we have this magnetic moment here, basically we have two kinds of forces. If we have this magnetic moment, let's say, in a constant magnetic field, the magnetic moment will try to align. It's the basic compass needle experiment. And when this magnetic moment here tries to align with a magnetic field, there is, of course, a torque trying to align. And if the field is constant, that's it. So the only force present is this torque that tends to align the magnetic moment with the magnetic field. If there is a gradient, if there is a gradient of field, if the field has different values through the space, there is, an attraction force between this magnetic moment and the place in the space where the magnetic field is higher. So these are the two kinds of macroscopic forces that we can expect from things like a magnetic nanoparticle. So a torque and a force in the presence of a gradient. Okay, and so we have this magnetic moment, and of course we have this force that tries to align it with the field, and at the same time we have, of course, the influence of the thermal energy. And the influence of the thermal energy, it's of course important. In the case of paramagnets, it was first measured in the case of paramagnets, and it's of course also important in the case of the magnetic nanoparticles. So basically, in the presence of a magnetic field, we have different energy levels depending on the spin. This is just an example of a spin 3/2. So we have these 4 energy levels. And of course, at very low temperature, just this one is populated. And when just this one is populated, it means basically that we are what we call in saturation. So the magnetic moment is aligned with the magnetic field. As soon as we turn on temperature, of course, there is enough energy such that higher energy levels are populated, which means that we will see, a decrease of the net magnetic moment of the system. So on one hand, the higher the magnetic field, the larger this separation between these energy levels. But of course, the higher the temperature, of course, more levels are populated. And of course, if all these levels are equally populated, we come up with a very small magnetic moment or magnetization of the system. And it's important. So what is here in play is a balance between thermal energy and magnetic energy. And so there are two fundamental constants here involved, which is the Boltzmann constant, which basically we cannot change. And here it's the Bohr magneton, which is, sorry, let me come back, which is basically this, the Bohr magneton, it's basically this ratio between the charge and the magnetic moment of the electron, which is something that, of course, we cannot change. And you can see that, so at let's say at 300 Kelvin, this is the value of the energy. And at the 7 Tesla, when we have 1 Bohr magneton, we have this energy here. So the thermal energy clearly dominates over the magnetic energy at the temperature that we live and with the fields that we have at hand. And 7 Tesla is already it's already a very large field. So compared to thermal energy, the magnetic energy of 1 UP, which is, let's say, basically 1 electron or something of the order of that. So the magnetic energy of 1 electron in the place at the temperature and at the magnetic fields that we have, it's very small compared to the thermal energy. And this is also why, this is the reason why magnetic nanoparticles, they are very useful compared to ions, like iron or gadolinium or chromium, because basically in magnetic nanoparticles, what we are doing, we are multiplying this energy by the number of spins that we have there. So we can have, thousands of spins in one magnetic nanoparticle. So if we multiply by the number of spins that we have in a nanoparticle, that's how we can bring this number here up to -21 or -20. And that's how we can overcome thermal energy. That's how we can get to saturation. That's how we can get our magnetic nanoparticles to be observed in MPI. So we can get this nonlinear behavior, of course, not with paramagnets, just because we are living at 300 Kelvin, and there is this fundamental difference between thermal and magnetic energy. So we need all the spins to come together, to have enough energy to overcome the thermal energy. So the question is what happens there? So here I am talking about the energy of single spins, which happens like, in iron salts or gadolinium chelates, just as the ones that are used as contrast agents in MRI. So these are single ions. So how do we come from the magnetism of a single ion to the magnetism, to the collective behavior that occurs in what we call a magnetic material? And it's again a gift from electrons. So electrons are fundamental in magnetism, because they have here, the lower mass that gives a large magnetic moment for a given angular momentum. And also electrons are able to exchange information, let's say. So the reason, because you end up with materials where we have one spin here, let's say, and another spin, let's say, in the same direction, it's because, electrons can directly or indirectly, they can exchange energy, okay? This is a simple ideas about direct exchange, which can occur in metals. Typically, it doesn't occur in oxides, but the idea is that, this electron has, like its orbital, which is basically its home, the place where it can exist, let's say. And this one has also, its orbital. And when these atoms come together and when the electrons come together, of course, you form something which is not the atomic orbital, it's a molecular orbital, and it has new levels. And among these new levels, you can have the possibility of this electron to come into this side, let's say. You also have the possibility of this electron to come in this side, and it can happen. So all these combinations we can write in a matrix in this very simple system. And basically, just to give you a general idea, we come up with these situations. A situation where, the most variable, the thing that happens most is that this electron comes on this side or this electron comes on this side. And if this is the case, then automatically the lower energy is that this electron has this orientation such that when it comes from, let's say, from this atom to this atom here, it already has, the good direction to fill in the same orbital. Okay. If on the other hand, so this means that, it's these terms here that will dominate. If on the other hand, the most, probable thing to happen is that they both exchange. So there is a direct exchange. Then in this case, we end up with this kind of configuration. Okay, so this guy, let's say, goes over there and this guy comes over here, and we end up with something that it's something like a ferromagnetic material. In this case of one going to the other side or this one going to the other side, basically, if this dominates, we end up with an antiferromagnetic material. If this dominates, we end up with a ferromagnetic material. This is just to give you, a very brief idea of the reason why there is this kind of interactions, which are called the exchange interactions. It's related to, let's say, to the traveling of electrons. It's related to the fact that there are molecular and crystalline, orbitals, and not just a simple atomic orbitals. So this can be directly, this can be indirectly, this can be mediated. So this is another example of an oxide in this case. I think I will not go into detail. It's this idea of going, electrons going from one orbital to another orbital, and what comes from there in terms of energies. Okay, so ordering. So instead of having single moments, single atomic or single electron moments, we have, correlation and we have exchange such that we can have ordering of these magnetic moments, which is what happens, for instance, in the magnetic nanoparticles. Of course, order has its limits again, and one of these limits is temperature. You can imagine that there is again an energy associated to this ordering, and of course there will be temperature, and there will always be a temperature that will match and that will overcome this magnetic energy. And when we arrive to that temperature, the system will no longer be ordered. So every magnetic material will have a transition temperature. So above which we will just have the paramagnetic isolated atoms, and below which we will have ordering. Okay. So when we speak about magnetic nanoparticles, normally we are working in this range here. So we have some sort of an ordering. So the spins, there is a dynamic. There are always some dynamics in terms of spin waves and these kind of things. But basically, we can imagine that the spins are aligned in one given direction when we use our magnetic nanoparticles. And of course, this order has also limits, and you are probably aware that in many magnetic materials, the system breaks into domains. The system breaks into domains. So instead of having one single domain with all the magnetic moments in the same direction, the system breaks like, in domains like the ones that I have here. And it breaks because let's imagine the case of a ferromagnetic ordering. So I have spin here, I have spin there, and these spins, they are in this direction because in terms of their in terms of the energy of that orbital, it's the most variable, it's the best, it's the lower energy thing to have them in the same direction. But this is about orbitals. So it's something like it's very short range. It has the range of the orbitals. On the other hand, if we go back here, moments tend to align with the field. And this is a very large range order. It's a very large range interaction. So on one hand, we have this interaction which is related to orbitals, which is very local. And at the same time, we have this interaction where we have a magnetic moment here that produces a magnetic field over there. The magnetic field curls. That was, the Maxwell equation. So it means that here, this is the direction of the magnetic field. So of course, if I have a second moment here, this moment will try to align with this magnetic field. This is a magnetic moment one. This is another magnetic moment. This is the magnetic field created by this one. So they will try to align. We call these dipolar interactions. So, and they are very long range. So in the long range, this will dominate, so that's why they try to couple like this. It looks like antiferromagnetic, but it's not antiferromagnetic, in the sense that it's something related to the orbitals. It's something that it's macroscopic. It's something that's related to this dipolar interaction here. So in the large length scale, this will dominate. And of course, those who will pay the price are those here. They will not be, in the alignment that the orbitals want, but, it's an energy balance. So if the total system can reduce the energy, that's fine. The ones here on the borders, they will pay the price, but the system will be in an equilibrium because, the total energy is decreased. Okay, so magnetic nanoparticles, they are just on this characteristic size limit where it doesn't compensate to break into domains. So we will always have something close to a single domain, and at least we can, the most, it's a good model in the most cases to assume that inside the magnetic nanoparticle there is just one single spin, which is the collection of all spins. And then, of course, we come back to what we wanted here. So we multiply this product by the number of spins that we have in the magnetic nanoparticle, so we can overcome thermal energy and we can get the system to the saturation. So it looks like a giant paramagnet. So that's why it was called superparamagnetism. So let me just jump to this slide here. So that's what happens. We will always have a TC. So in the limit of, let's say, very high temperature, it will turn up into a collection of paramagnets, but we are not working there. I mean, when we use our magnetic nanoparticles, we are basically working here. So they work like a single giant spin, as you know. And this was first observed by Elmore, I think, working at IBM. so back in 38. So this was the first, magnetization curve of superparamagnetic nanoparticles. I think it was nickel back then. And then it was the first time that this equation, Langevin came up with this equation by the beginning of the 20th century. He was trying to fit this equation to paramagnetic materials, but paramagnetic materials, they don't follow exactly this equation because they have, a quantified number of levels. They don't have, so they cannot have all the directions in space. So the first time that there was, a material that could, somehow fit to the equation, which is the line here, Elmore put. So this line here is this Langevin equation. So it took like, something like 40 years to find a material suitable for this equation. So basically here we have, the set magnetization, which basically depends on our material. So if we want to change that, we need to change our material. And this magnetic moment, which is, the of the magnetic moments that we have inside the particle. So that's how we can enhance, that's how we can enhance here the magnetic energy. So that's how we can bring it close to saturation using lower fields. It's by having higher magnetic particles with higher magnetic moment here. And so in that case, we are here in this range, which we call unblocked superparamagnetism. And unblocked because of the following reason, because it's a collection of spins. Sorry, let me jump. It's a collection of spins, but it's a collection of spins in a crystalline lattice. And in this crystalline lattice, the interaction between the spins and the lattice gives an extra term of energy. It means that the energy of the magnetic moment is angle dependent. It depends on the angle between the moment and the crystalline axis of our material. Here are, just iron, cobalt, and nickel, very simple materials. And here it's the energy of this interaction between the magnetic moment and the lattice. And it shows us that here, if the magnetic moment aligns here, can you see here sort of a dip, and here a sort of a dip? So if the magnetic moments are in this direction, they have lower energy. And of course, it's a cube. It's a cubic symmetry material, so this direction is equivalent. It's equivalent to this one over here. It's equivalent to this one over here. So whenever the spin is here, is in a minimum of energy. Whenever the spin is somewhere here, it's in a maximum of energy. So cobalt is a uniaxial system. So here I have a minimum, and here I have a maximum. And nickel, it's also a cubic symmetry system, but it's the opposite of this one here. When we have here a minimum, here we have a maximum, and the opposite here. So which means that, if I plot this as a function of angle, I come up with this, thing here. So I have a minimum of energy in two opposite directions, and I have a maximum of energy in between. Okay, so, so then we have, in this temperature range, the system doesn't see that energy, that energy landscape. Okay, so so this is a very simple energy landscape, a minimum here, a minimum here, a maximum here. So in this temperature range, let's say the thermal energy, it's something like, it's very big compared to this energy here. And that's when we have, that's when this Langevin equation is valid. The system doesn't see the energy landscape. So the system doesn't see this energy landscape. And it means that the magnetic moment can freely fluctuate in any direction of space. let's say it's a super paramagnetic system in a sense, okay? But as we cool down, or as the, okay, so as the thermal energy becomes of the order of this energy, then something else occurs here. So this expression is no longer valid because this expression takes into account that every direction in space has the same energy. And then we have something like this here. So instead of having a Langevin equation, we have something like here, or here, this is the Langevin equation here, and we have something like this. When we are here, which means that, so the energy landscape, okay, starts to have an influence, which means that the spins start to fill this energy landscape when they fluctuate in space. And basically, in practical terms, it means that it makes more difficult for us to get into the saturation, okay? It makes more difficult to come into saturation because this energy landscape starts to appear. And here we come into the region where the system is blocked. So where the system is blocked, it means that, and I come back to here. So here it's a temperature. Here it's the two states. So I have here, let's say, a positive and a negative, let's say left or right state. Okay, at this temperature, the system is fluctuating. Okay, so he spends more time over here because probably, you know, these energy levels, they are not equal. There is, you know, there is an external field that favors one of the directions. And then when we start cooling down, the system starts to be freeze, to be blocked in one of these directions. And if we cool it down again, you know, most of time it's in one direction. If you would cool it even down, let's say, let's put here 0.1 Kelvin, the system would be always in one of the directions. So the system would be blocked. So our nanoparticles will be blocked below a given temperature. And it really depends on the relation between this, you know, this energy gap and the thermal energy. So that's why this blocking temperature here, is, sorry, I should have, oh no, it's not here. You know, but it's, so it's the nail, sorry. So this blocking temperature here, when we have this nail mechanism, it's basically, you know, the exponential of this thermal energy, which we write as a constant times the volume divided by the thermal energy here. So so this is basically the characteristic time for this you know, for this relaxation between energy minimum. So sorry, I think I will just so of course that this single particle you know, framework, it explains most of the things that we have with the magnetic nanoparticles. Of course, you know, of course we have deviations, some of the deviations related to surface atoms. Many times it occurs, so these are megamite, and it's all megamite made by water-based synthesis. So it occurs in this kind of systems mostly. So we have a decrease of the saturation magnetization, and of course of the magnetic moment, just because we have some surface atoms that have a very low contribution to the whole magnetic moment. Also, we have dipolar interactions. Here it's a TM image of some magnetic nanoparticles. And on this TM, you know, image, you start seeing things like, you know, like things like this. So, which we believe it's due to magnetic interactions, you know, basically probably the magnetic moments or these nanoparticles, they are aligned. And when they are aligned, they close this loop. And when they close this loop, they give a very good path for the magnetic flux. So the magnetic flux, instead of being out in space, it's inside this magnetic material. So we have a save of energy. Sorry, this is not an exercise. This was meant, it's something that was here for my students. So this, this dipolar interaction, it's what I've written before. I have a magnetic moment here. So this magnetic moment produces, a space and a direction dependent magnetic field. So if I have another magnetic moment here, it will align like this, just because the magnetic field is pointing in this direction. If it's somewhere in this part of the space, then the interaction will be like this. So in this part of the space, they will try to align anti-parallel. In this part of the space, they'll try to align like this. So this is dipolar interaction. And of course, when we have more concentrated system, we should always expect dipolar interactions. So this is my last slide. So here, if the system is blocked, it means that the magnetic moment of the nanoparticles, it's in one direction, so it cannot cross this anisotropy energy. And of course, we will have remnants, we will have coercivity in the magnetization as a function of field. We will have this. Of course, here we will not have this, and for MPI, I mean, we want to have something like this. We want to have a nonlinear contribution, so we want to be not here. This is the linear part, so we want to be right here. So we want very simple and nice systems here. Of course, this unblocking can be by the nail relaxation. I didn't talk about this relaxation, which is relaxation in fluids. So here it's just, the viscosity of the medium. And of course, if we put temperature high enough, the order between the magnetic moments inside the nanoparticle, the order will be destroyed, and we end up with a paramagnetic system. So I think this is it, and I think I have stretched my time, so it was
thank you for the presentation. Finally, a good physics introduction. Thank you. No, thank you. Good physics on magnetic nanoparticles as well. Let me see. Do we have any question at this point from the audience? Raise your hand, unmute yourself, or type your question. While we're waiting for other people attendees to ask the questions, I would be curious to understand your view on, let's say, three-dimensional distribution of nanoparticles and influence on, let's say, resolving power and resolution when we talk about MPI. And in my view, I would be having like monocore nanoparticles, nanoflowers as something else, and then again, the chains of monocore nanoparticles, and they come more and more into practice these days. So my question to you is, what is the physics besides the differences in monocore nanoparticles, nanoflowers, and chains when it comes to resolution and resolving power in MPI?
Yeah, thank you very much. It's a very good question, and it's very simple to speak about very simple systems, as the one I presented here. When you start with more complicated systems, then these things start to break down, and the models start to be more complicated. And I mean, when you come from the single spins and from the single, from the single magnetic nanoparticles, it's all easy. When you come from bulk materials, I would say that it's also, feasible. And there is, this room in between, which is difficult to address in terms of macro spins models, and it's also difficult to address in terms of computational models. But your specific question about resolution, I would say that, let's say that in practice, maybe if you measure your magnetization curve, probably you have your answer. So I would say, and I see here Patrick and people that knows about this much more than myself. So if you can get these particles, these systems to saturate, the easier they saturate, I would say that the point distribution function will be narrower. So
are we defining the resolution in terms of PSF in that?
Yeah, the contribution, because I would say that from the point of view of the nanoparticles, I would say that, if they approach to saturation at lower fields, I would say that you would expect to get a higher resolution, at least from that.
And which of those three thank you. Which of those three examples would reach saturation earlier at the lower magnetic fields? The monocores, nanoflowers, or chains?
I mean, chains. If you have chains of dipolar interaction, I would say we have to measure. Measure would be the best things to do. In theory, if you have larger cores, if you have larger magnetic moments, then you would saturate them easily. So, larger magnetic moments makes moments higher. So even if we look at here at this Langevin simple equation, it makes saturation easier. Bipolar interactions, so they do the opposite in general terms. So they try to to put everything closed inside the magnetic nanoparticle, so you have an extra energy to bring the moments to saturation. So I would say dipolar interactions will make it harder to saturate. But I think when you come to more complicated systems, I would say you can expect things, but you also can get unexpected results. So
that often happens indeed in experimental setting. Before we go on or not on this item, there was a question in chat from Serhat. Can you please elaborate how and why the area of hysteresis curve is proportional to SAR, and what is the source of the heat we get with MPI hypothermia? I'm sorry, Nuno, you muted.
Sorry,
Yes, so, go ahead. Do you need me to repeat the question?
No, sorry,
Great.
I got it. So let me come back here to this magnetic energy here. So there is the product of a magnetic moment and a magnetic field is an energy. The product of a magnetic moment and a magnetic field is an energy. So it's always an energy. So if I put the product of a magnetic moment and a magnetic field, this is an energy. In fact, this will be a density of energy because I'm putting here saturation magnetization. Which kind of energy? Then, it depends. So it means that this area here, which is the product of magnetization plus an H, so if I multiply by this constant, this area here will be an energy. And of course, it's the energy that it takes, the system, if it's doing an hysteresis, it means that it's using two ways of coming back. So it's dissipating. It's dissipating. I think you can understand that it's dissipating.
So if I'm trying to summarize what you just said, when we are using a fluctuating magnetic field, and the area of the hysteresis loop, what we're talking about here, represents the energy loss for each cycle, right?
Oh, exactly. So the power is just the product of that area times the frequency that you are cycling.
And usually, I'm not sure it's 100%, but the energy loss in this case, in case of alternating magnetic field applied, it's manifested in heat, and therefore, by measuring heat, that's the relation between the hysteresis and SAR. Is that
Yes.
sufficient answer, Serhat, or do you have any more questions? There was a question from the audience. Yeah,
That's probably you know that paper for Rosenvik. Sorry, I'm not. There's a JMM, Journal of Magnetism and Magnetic Materials paper, and that's really explained there. So it starts with an energy, and the energy goes to the power, and then it gives you, this linear, it expresses the power in terms of susceptibility, of saturation, magnetization, assuming that this response here is linear. So basically that you have some oval response here. But it doesn't matter if this hysteresis comes from domains, wall movement. It doesn't matter if it comes from nail relaxation. Doesn't matter if it comes from Brownian relaxation. As long as there is an hysteresis loop, and this hysteresis loop, it's also frequency dependent. Because this is a dynamic phenomena. So typically, if you cycle your field faster, then the coercivity, it's not a fixed value. The coercivity also depends on the on the frequency of the magnetic field. So, but it doesn't matter where the hysteresis comes from. This area will always be a dissipated energy. And typically it is dissipated, transforms into heat, lattice vibrations, heat. So it's
Thank you, Neo, for your answers. Are there any other burning questions from the audience so far? I could keep asking questions, because I always have questions about the physics, because that's not I'm electrical engineer by trade, so that's not my strongest let's say research strength. Interested is, but no one covers everything, I suppose. Any other questions from the audience? Burning questions at this point? We're kind of reaching an hour in the webinar. For my part, we could still stay longer if
I think
they
I
are.
just so if no one has any other questions, I'd like just to ask for a curiosity, because not only me but other Nuno students, because in one of the slides he put a photo of the 6 ways travel makes relations stronger. So I'd like an explanation, like the relation of these, if
this is
possible.
sorry, it's just it's just something that I normally show to the audience. It's just for fun. So it's just to give you the idea that, so when we have magnetic, because people and books you read about magnetic exchange interactions, but I mean, where does it comes from? So it basically comes from the fact that the electrons live in orbitals, and these are molecular or crystalline orbitals. So basically, it means that there is a probability of an electron to be somewhere which is not its original atom, and somehow, so it means that the electrons, there is this exclusion principle that they cannot be in the same level with the same spin direction. So this makes a constraint on the direction of the spins of the electrons. So if you wouldn't have these molecular or crystalline orbitals, of course, we wouldn't have matter. We wouldn't be here. So it's really about about the chemical bound. There is a very nice book from John Goodenough, which is Nobel Prize. He got a Nobel Prize on batteries, but he wrote a book about magnetochemistry and magnetism and the chemical bond. So magnetism, exchange, it's really about chemical bond, and chemical bond is about molecular, orbitals. So it's about of this possibility of the electrons to be, displaced, not in a single atom, in a molecule. So you would never have this collective magnetism behavior with protons, because protons, they cannot just travel. I mean, somehow. So it's about this possibility of electrons to travel.
Thank you so much for the answer.
Thank you. Thank you for the answer. And if they are, I'm just waiting. Apparently, there are no other questions from the audience. Nuno, thank you so much for providing information on physics, presenting here. Thank you all for attending this webinar on nexMPI, trying to, let's say, provide as much information as possible to wider audience as well. We will be having a new webinar in 4 weeks again. Please stay tuned while we're waiting for the next presenter in 4 weeks. Thank you so much. Have a nice evening, afternoon, or the morning, and see you in 4 weeks. Bye-bye.
Thank you all. Bye.
Bye, thank you.